light hits it, and it'll get to these components. Now again, the eluent, the gas or the water or the solvent that flows through will not fluoresce, but your components will. So your light will hit it, and these little things will take in that light and give off light at a different wavelength. So it'll hit this, and it'll send out light in all different directions, but your detector is 90 degrees away. You have your detector right over here. Well, the light going in might hit it, and we don't really want that to happen. We'd rather have your light that hits it not hit the detector directly. So your light hits it. Your components will fluoresce. They will give off a different wavelength of light. You'll detect it at 90 degrees. When it detects that different light, it knows something's coming through. And this is very, very sensitive. The fluorescence detectors are very, very sensitive. We can detect even minute amounts of our component in there. So that's why we can use fluorescence detectors. But once it detects it, it appears as a peak in the chromatogram. Which you would see over here. Here's, let's say, it's light shining in it. Suddenly, it says it's fluorescing at a different wavelength. The detector's detecting it, so it's going to give a good signal here. That's how that one works. Okay, the IR is more complicated. I don't have a picture. I can't really show you a picture of what it looks like. It's because it's more complex, the signal, but that's the point. You send, let's say, an IR, let's say you hit it with infrared beam, but not only do you detect the fact that the light is weaker, we know exactly where it's weaker. We know exactly which wavelength it's weaker at. So if it's weaker at certain wavelengths and storing at other wavelengths, only certain molecules will ever do such a thing. So we can match up here. Let me just show you here. This would be an IR signal. Whatever, you send the light through, and we realize it's absorbing a lot over here. There's that 3,500 wave numbers. We're not going to talk about what wave numbers are. They do relate to the frequency of the light, and and they also relate to the wavelength of light. But never mind. This is just what the signal would look like. This is an infrared absorption signal. Absorption spectrum, actually. So it absorbs a lot over here, a little bit over here, a lot over here, and not much over here. Here we got, I recognize this is a stretching of the CO band, but never mind all that. And again, all bunch of stuff over here, all different. This, by the way, is called the fingerprint region. It's called the fingerprint region because every different compound has a different number of these peaks in different places. So what we do is we have a whole table of all our thousands or who knows how many, even millions. I don't know how many we have. I think we got into the millions, but I'm not sure. Anyway, we have a whole table of where the bands are and how big they are and how relative to what. So when the IR signal gets into your sample, it'll produce this. Rich with information. We can certainly look at this fingerprint region and say, hey, that looks exactly like, this item in the table. That I know is heroin. So when the thing is flowing through the chromatogram, flowing through the column, we're hitting it with the IR light. The signal we're getting is not just a single band, but it's all these things. These things are matched to pure spectra that we know, and we can actually find out what the thing is. It might be gasoline. It might be fentanyl. I don't know. Whatever it is, we are getting this we're getting this information from this chromatogram. Let's take a look at this. We know it's absorbing, so we know that it's coming through. But at the same time, we get the signal. It feeds into the other part of the detector. It's not only that something's coming through, but what's coming through. We get right over here. We're going to be seeing this signal, and we're going to be able to identify, oh, that is heroin, or that is fentanyl, because we recognize the way these peaks are. So that is the IR, the difference in IR and absorption and ordinary fluorescence. Ordinary absorption fluorescence will say it's coming through. IR will tell you exactly, will give you a signal that we can use to find exactly what's coming through. So the wavelength absorbed and fluoresced are characteristic of the compound, but not unique. For absorption and fluorescence, they're not unique. Some absorb at different wavelengths more than others. That's true, but many of them absorb at the same ones. So they are characteristic, but not unique. The IR, however, with something like this is unique. This pattern of what it absorbs and which wavelength is unique to every compound. So, whoops. Okay, so, and as we mentioned, that part of the IR spectrum, in fact, it's this part, right over here, is called the fingerprint region because it's unique to every compound. Now, it's not just that. I don't know, again, it's not more complicated, but mass spectroscopy, we can do the similar thing and get something similar to, it doesn't look like this. It's more like straight lines. They're more, separated from each other. But you also get, a lot of signal, a lot of different peaks from a mass spectrometer. Now, the thing about mass spectrometry, we'll look at this for now. What it does is you take the component. Let's say you separate it using the gas chromatogram, using the gas chromatography. So you get it, you know it's separated. Then so it's separate. Then it goes through a mass spectrometer. A mass spectrometer, I don't want to get too complicated. It shoots your molecule. It shoots your molecule, through itself, and it finds out how fast it goes. The bigger it is, the slower it goes. The smaller it is, the more speedy it is. So it can tell the mass of your molecule. So you can use it. In fact, that's why it's called mass spectroscopy or mass spectrometry. It tells the mass of every molecule you can think of. Now, again, it's a little more complicated than that, but you can certainly tell the mass of any molecule. So it can tell the mass of heroin is different from the mass of gasoline. The mass of cocaine is different from the mass of fentanyl. So you can certainly tell different. Not only can you tell that something's coming through, you can also tell the mass of what's coming through. And therefore, you can identify different molecules. Now, different molecules may have the same mass, so it's not unique, but enough of them have different masses for it to be good enough. Furthermore, not only does it measure the mass of your molecule that goes through, your molecule often, in this process, it breaks apart into small pieces. It can tell the mass of the pieces. Now, this is pretty much unique. Not exactly unique, because if the mass of the whole molecule is 1, and the pieces also are known, then we can put the two together, the mass of the piece of the mass, and this is usually, I would say most of the time, it's unique, especially for more complicated molecules. It's unique for each one. So, you